Check it out now, y'all.
nanoHUB-U, online instruction.
Hello, welcome to week 5. This week we are looking to do a review of some of the recent advances in thermoelectric materials and physics. Let me start the first lecture about Thermionics versus Thermoelectrics. This is something you heard in week 2 in Mark Lundstrom's lectures when you were discussing thermoelectric effects in short leg devices. There is different ways to introduce the problem. Today I want to introduce it with an analogy of something very different, which is vacuum thermionic emission or vacuum emission. Basically, if you have a hot cathode separated by a cold anode, vacuum is an energy filter. Basically, the hot electrons from the cathode could be emitted and go to the anode, but the cold ones are blocked. And whenever you have some sort of energy selection, you can do work. If I put hot and cold electrons in equilibrium or in contact with hot and cold electrons in the lower temperatures, without energy selection, they come in equilibrium, but you don't do any work. To do real work, you need some selection, and vacuum does that. This is the principle of actually electron emission in vacuum tubes used in old TVs. In 1950s and 60s, there were ideas of using this for space power generation. Basically, if you have materials with appropriate cathode and anode barrier heights, and the barrier height should be adjusted based on the temperature of the cathode and temperature of the anode so that the appropriate hot electrons move, but the cold electrons are blocked, then you can get very high efficiencies. Hastopoulos has a nice textbook, 2-volume textbook on this vacuum thermionic emission. Jerry Mahon in 1994 suggested similar type of vacuum devices could be used for cooling, but only at high temperatures. Why? Because the work function, this barrier height to vacuum, is typically large, so you need very large temperatures to be able to observe appreciable current. One limitation is this barrier height and how much it can be lowered. If you want to do vacuum thermionic emission at room temperature, you need this barrier height on the order of kT, and having stable materials with low work function is a challenge. But there is a second challenge. Electrons that are emitted from the cathode, they go to a vacuum region. They have a net negative charge because there is no doping or positive ions in vacuum to work with. So this creates a space charge effect, an additional barrier that needs to be overcome. Often this barrier needs to be less than a micron if we want to neglect that. There is ways to manage the space charge by adding ions in the vacuum, and this is something that is done, but then there are complications about stability and how these ions migrate and so on. In 1997, one of the ideas that we proposed was, let's do this solid-state thermionic emission. Basically, you can make barrier heights easily in the kT range using heterostructure barriers. So by having a degenerate semiconductor or a metal, a solid-state barrier, and a degenerate semiconductor or metal on the other side, you can mimic what is here. The big advantage is you can adjust the barrier heights to get the right balance at room temperature or even lower. The disadvantage is now you have a solid between, so you have the heat conduction from the hot and the cold, which is bad if it's happening through lattice. But there was some kind of confusions early on, because in the original paper about single barrier devices, the whole focus was nonlinear regime. Basically, the bias so large that we are dominated by the current from the cathode, the back current can be neglected, and in this paper it was shown the high power densities could be achieved. A year later, Jerry Mahon and co-authors mentioned that a multi-barrier solid-state thermionic device could have high efficiencies in a linear transport regime. But later on, a couple of other authors, as well as Jerry Mahon himself, went back and said, really, that actually doesn't improve the efficiency. So that's something that, what is the relation between linear and nonlinear? That's something we want to discuss today. But the basic idea is selective emission of hot electrons over a barrier can cool emitters by evaporative cooling. And thermodynamic reverse process can generate power. Again, when I talk evaporative cooling, if there is a phase transition as electrons evaporate, the latent heat has a big impact. For the case, that's what happens in a regular evaporative cooling using, for example, sweating. But in the case of electrons, we don't have that phase transition, no change in degrees of freedom. So let's look at this thermionic versus thermoelectric first for a single barrier device where something is on the order of microns. If the barrier is thin and the smaller than the electron relaxation length, then you have some ballistic movement. This is a regime which was described easily by the Landau formalism you saw in Mark Lundström's lectures. In this case, you cannot define a Seebeck coefficient independent of the contacts. This is really as a whole device, you can define what is the junction or ballistic component to the thermoelectric transport. If now I put lots of tiny barriers in a superlattice, and now you have a device that is longer than electron energy relaxation length, but inside of it you have metals or different layers that are smaller than the electron mean free path. This could be a linear device as well. So in the linear regime, a linearized thermionic, another way of looking at it is a thermoelectric device where the properties are modified using this heterostructure. So again, thermionic can be looked at as thermoelectric in the linearized regime. What are the key differences between thermionics and thermoelectrics? Thermoelectric property cooling is a bulk property, is manifested at interfaces. Basically is the average energy of the moving electrons when they move from A to B. If electron gas expands or contracts, absorbs some energy, that's Peltier cooling and heating, or in the case of Seebeck effect, is electron gas that is doing the work. Thermoelectric is usually described in a linear transport regime. In week 4, we described some of the cases that if you apply large enough voltages or large enough currents, you could be in a nonlinear regime. This is at high current. This is the work by Mona Zebarjadi and colleagues. Also inside a bipolar device, you can have a nonlinear thermoelectric effect because there the quasi-Fermi levels change with bias. But all of these are can be treated differently than how you would treat a solid-state thermionic device. Because in a solid-state thermionic device, the barriers, the junctions matter, is an interface effect. In the case of a single barrier and nonlinear transport, you can get high cooling power density. That's what is described in these early papers. In the case of a multiple barriers and ballistic transport, as I mentioned, Mahan and colleagues mentioned that high efficiency could be obtained, but later on, Ulrich and others mentioned that really the advantage is only due to the low thermal conductivity, and that's something that I want to question in today's lecture. Then there were a series of papers that we initiated on tall barrier superlattices, why there should be advantages. Experimentally, there were results on indium phosphide and silicon germanium based thin film coolers. Cooling power densities of more than 500 watt per centimeter square were demonstrated. You saw that in week 4. I want to also show how the physics of this is related to others. And finally, in the case of ultimate metal semiconductor superlattices, there is potential to get higher efficiencies, and I want to basically explain how one could be in different regimes. Let's start with the fundamental trade-off that exists in any bulk thermoelectrics between the Seebeck coefficient and electrical conductivity. And that can easily be explained using the simple density of states. That's a key component that contributes to the transport function you saw in week 2. If I have a material at low enough doping so that the Fermi energy is near the band edge, by just looking at the curvature of this curve, you can see the number of electrons with energy above the Fermi is significantly more than the number of electrons with energy below the Fermi. As a result, within the Fermi window factor, the average energy of the moving electrons is different from the Fermi energy and is given by basically a slope of the density of states. What happens if we take the same material and we just add more and more dopants? This Fermi level rises. As the Fermi level rises, what you see is that this density of states become more symmetric. In the limiting case of a almost metal or a degenerate material, you have lots of electrons in the material, but this distribution is symmetric with respect to the Fermi. That means the effective Seebeck coefficient, the average energy of moving electrons with respect to Fermi, is almost zero. And that's a challenge, how to get high conductivity and high Seebeck at the same time. Conceptually, then, as I mentioned, symmetry of density of states near the Fermi energy is a key factor. How about having a material that is a metal, but somehow we make all of the hot electrons with energy above the Fermi easily move, and the one below are filtered. They cannot move. How that can happen? For example, one could imagine a multi-layer. So you have a big component of the multi-layer, which is a degenerate semiconductor or a metal that provides a lot of electrons, but then you have a barrier exactly adjusted within kT of the Fermi energy so that electrons above can easily move, but electrons below are reflected. That's kind of the idea of how to break the symmetry between Seebeck and conductivity. And again, when we are talking in this case, is an effective thermoelectric material. Each of these barriers is on the order of electron mean free path. That's what makes sense. That's what is needed to get this filtering. But we don't want to run it in a high voltage or high current case. It's not a nonlinear case. We can still define an effective Seebeck coefficient. What is the potential of this? That was the basis of a center we had for quite a few years, Thermionic Energy Conversion Center. If one could take a metal with a large Fermi energy on the order of a couple of electron volt and put perfect electron filter, ZTs of 2 to 7 would be possible, even with a lattice thermoconductivity of 1 watt per meter Kelvin, that is low, but that is achievable, and an electron mobility of a typical metal, which is 10 centimeters square per volt second. So that's kind of what was the motivation why this effort was started. The calculations are based in this paper in 2004. And as a result, we had a diverse group. How do you make such a metal semiconductor composite? You need material scientists in order to understand phonon transport, thermal transport. You need mechanical engineers for electrical transport, you need physicists and electrical engineers, you need to make devices out of it. So that's where this diverse team came about, and we worked for almost 9 years toward it. And I will explain later this week about some of the main lessons we learned. Of course, unfortunately, we did not get to these ZT numbers. That's a big challenge. But by working on this, we learned quite a bit about what are the factors that dominate the power factor in materials as well as the thermal conductivity. If you compare the calculation in this paper to some of the calculations that were in original Mahan's 98 paper that are actually shown in recent thermoelectric textbook, you see very different numbers. Here are some efficiency of a multi-layer thermionic device plot against the barrier height at different source temperatures. what is used here to get this type of efficiency, you see a couple of 8 to 10%, is Richardson equation, which basically tell you thermionic emission goes with exponential of a barrier with a prefactor that is proportional to the temperature square. If you linearize the Richardson equation, you get the TI figure of merit, and it was shown by Mahan and Vining and others that the TI figure of merit is always smaller than the TE figure of merit, and this is what is described in these main textbooks. So a question, how do you learn, is by looking the problem from different perspective. You say, how is this one tell you low efficiencies and this one tell you high efficiencies? Which one is correct? Of course, everything is in the assumptions that go into in the equations used. And an important point I want to make is that the modified Richardson equation that is used in these is not accurate to describe electron transport in superlattices when the Fermi energy is a few kT from the barrier height. That's a key message. This is valid when the Fermi energy is deep and is used in vacuum kind of emission and also in very deep well emissions. In the regime we are interested for thermoelectrics or for energy conversion or cooling, we need large current densities. Fermi energy need to be within 3 to 5 kT, 3 to 4 kT of the barrier height. In that regime, you cannot actually use this equation. So the equations that are used to derive this are different, are not Richardson equation. But every time you have a theory, you have to say how you are validating the theory. So here are the equations. The equations are described as in the original papers, what is called is differential conductivity. Through these lectures, you saw that this is actually directly related to the transport function. I presented based on the modified Boltzmann transport. It's always good to look at the same problem if you want to present it from a Landauer formalism, how you would formulate it. But basically, electrical conductivity as an integral of this transport function, differential conductivity that is energy dependent, sum over all electron energy give you total conductivity. Seebeck coefficient is the average energy of the moving electron with respect to Fermi with a weighting factor of differential conductivity. And electronic contribution to thermoconductivity has to do with the second order moment of this differential conductivity, or the width of the band. The key question to do calculation is, what is the form of this transport function differential conductivity you use? Here there are different levels of sophistication. In the original papers that came out in 2004, what we had assumed was a standard kind of Boltzmann approach, a relaxation time, a velocity for electron, density of states, Fermi window factor, but we added an energy filtering, which is a tunneling and band age discontinuity coming from quantum mechanical by hand. This is not a first principle derive, but the idea was that this is the number of electrons kind of in the window and how far they move, and this takes into account something about superlattice. With the advanced Landauer formalism, it is possible to do this more accurately. The other factor is, of course, Fermi window give you an optimum doping. Density of states, a key point in this original paper is both states in the well and in the barrier needed to be taken into account. And by considering both, we could explain experimental results in other samples. Later on in 2007, in this physical review B paper, we improved this by actually taking into account that whenever you have superlattice mini-bands, the velocity of electrons also is changed because of the mini-band effects, group velocity, and the energy scattering was introduced. And later on again by 2008, and so we introduced in the scattering parameters effect due to nanoparticles and so on. And we will see that later this week. How do you verify that this type of formalism can explain the data? Here is an example. There is a lot of data in the literature that describe current voltage in superlattices for applications such as quantum well infrared detectors. For example, in this case, some of the early work of Barry Levine is 50 periods of gallium arsenide, quantum wells 44 nanometer wells, 30.5 nanometer barriers, very thick barriers. Barrier height is 247 MeV because of the percentage of aluminum used, about 30%. The doping in the well, 410 to the 11, 10 to the centimeter minus 2. So the Fermi energy is within about 100 MeV of the barrier height. If you measure just the dark current, how much current flows into this in dark versus bias, you see a significant dependence with temperature between 50 Kelvin to 112 Kelvin, just 60-degree temperature change. The current in the device changes almost 8 orders of magnitude. The solid line, black line, is the experimental data measured by Levin. The dashed line are the theory that he used. And the circles, the red circles, are our theory based on this modified Boltzmann transport. You see we have a very good match over the wide temperature range and bias for this. In some cases even better than the original theory. One of the key things that we had to assume is lateral momentum of electrons is conserved as electrons move in this layer. And that's something I will explain later why lateral momentum is important. Interestingly, Levin, to get this curve himself, he assumed actually lateral momentum non-conserved, but he neglected the electronic states in the barrier. So it's interesting that even when you get fits in the wide temperature range and so on, is interesting what are the assumptions and implication of the assumptions. I think that this role of the barrier states are important and needs to be taken into account. Another verification for the theory was in the mini-band transport regime. So if now I have superlattices of indium gallium arsenide and indium aluminum arsenide with about 50% to indium concentration, lattice matched to indium phosphide, if the barrier is only 3 nanometer, neighboring wells are strongly coupled, so you form instead of individual quantized states, you form mini bands. The barrier height is huge, 520 MeV. So when you dope the material, electrons move between mini band rather than above the barrier. So it's a different transport regime. The question is, how does it affect thermoelectric effect? Here is quantum mechanical transmission versus electron energy for such a superlattice. In this case, we assume electrons are coherent over 2 periods. So you see a mini band, the blue one, at about 120 MeV, another mini band at 300 to 400 MeV, and this is kind of almost above the barrier, about 600. Sorry, by the way, this is the barrier. So these are the bands that you can calculate using standard quantum mechanics Schrödinger equation. 4 samples were studied, samples A, B, C, and D, with 4 different dopings ranging from 210 to the 18 to 310 to the 19. Large doping to very large doping, and you can see by changing the doping you can move from a place where the window factor is near the first band to the case where your doping is near the second band. So it's a very interesting, complicated structure. The question is, can our theory explain the measured transport properties? One of the first results here was actually to measure cross-plane Seebeck coefficient. You learn in week 3 how such measurements are done. I will show it to you a little bit. Here are Seebeck measured versus temperature for 2 different device sizes. Of course, it should be independent, but that's a verification. The dashed line is what the theory tell you for this doping, what the Seebeck versus temperature should be. The red line is the theory, what they tell you the superlattice should be. A very good match between theory and experiment. And here are the doping dependencies. I told you we had, this is the measured Seebeck and theory Seebeck for versus doping for samples A, B, C, and D. So what we have here is the superlattice curve is a non-monotonic dependence of Seebeck versus doping. For any bulk material, you increase doping, Seebeck goes down monotonically. For the case of superlattice, it goes up and down because of the mini band formation, and our theory and experiment match quite well. So this is an indication that a transport theory based on modified Boltzmann not only can explain electron transport in superlattices, can also explain cross-plane Seebeck. Just a quick reminder of how we measure cross-plane Seebeck. We had tiny heaters fabricated on top of a superlattice, as well as a reference. This is a top view of the heaters. Under the heater, we had an electrode, so you can heat up here, measure the temperature, and from the voltage measure the resulting Seebeck cross-plane. Again, quite sophisticated, but with the right device processing, one can achieve that. So this theory is good. One thing I want to mention is this role of the lateral momentum. If we just take a simplistic picture in space, if this is a dimension, I put multi-layers of a metal and some sort of a barrier, metal and a barrier. By eye, you would say, oh, the barrier are chosen so that electrons with energy above the barrier move and electrons with energy below the barrier don't move. When you look at this, you say all of the electrons with high energies move and all of the electrons with low energies don't move. Every representation has a limitation. This is a picture in energy space. A picture in the energy space only represents part of what is happening to electron. Why? Because electrons are moving in a three-dimensional space. If instead of energy space, I show electrons momentum in one of these metallic layers. So this is kx, ky, kz. Remember, z is the direction where we change the periodicity and add multiple layers. In x and y is the same material. If I have a metal, typically we have a Fermi sphere. This is the Fermi wave vector, the blue sphere. For electrons that have energy more than the Fermi wave vector is shown by this area of the sphere, which is basically with energy above the Fermi, and the ones below are below this, and that's what happened in the momentum space. When I add multi-layers in direction z, only electrons in this location can move, because this corresponds to lateral momentum conserved. Kz bigger than the k barrier is not E of the electron B than E of the barrier. That is a selection rule. Selection rule is related to this. Why lateral momentum should be conserved? There is a different way of looking at it. There is a translational symmetry in the plane of each of these layers. Every time there is a symmetry, there is a conserved quantity, and that conserved quantity is in plane momentum. But if the in-plane momentum is not conserved, then all of these electrons that are hot can also be selected, and that's something you don't see it in an energy picture. That's some of the lessons. You need to look at the problem from multiple perspectives. So planar barriers do not transmit most of the hot electrons. If the lateral momentum is conserved, we have a momentum filter and not an energy filter. Sometimes looking at the energy picture or a momentum picture could be misleading. You say, what really is happening to the hot and cold electrons? You can see their impact even in the case of a real space. Assume I look at from the top of a metal where hot and cold electrons are in equilibrium, and I put a hot electron filter, material with some sort of a barrier. If I look at this, you see some of the blue arrows. They are supposed to show electrons with low energy, cold electrons, and some electrons with larger arrows, the red ones. These are the hot electrons. I made a filter here, so I want the hot electrons to go on the other side. But what you look at here is that in addition to these hot electrons that go through, you have these hot electrons that are totally internally reflected. This total internal reflection is this electron is hot, but in the direction perpendicular to the barrier doesn't have enough energy to go the barrier. That's exactly what happens in optics when you go from low to high index material. Total internal reflection is an indication of lateral momentum conservation. And that's kind of what is the main problem. How could you break that total internal reflection? As I said, it comes from symmetry. A simple idea is between the emitter and the barrier, let's break the symmetry and make it a zigzag kind of non-planar barrier. It's kind of complicated to model this using analytical equations, but you can use a Monte Carlo. A simple Monte Carlo here shows the populations of electrons in this structure top view. You can see lots of electrons in the emitter, and you can see nicely the zigzag barrier, and some of them are emitted above the barrier. We chose this barrier to have a specific height. Here is the energy versus distance as you move in this direction, and you can see lots of electrons, both low and high energies in the emitter, but in the barrier you only have the hot electrons. So when this is a way you can break this translational symmetry. The idea here is almost kind of analogy with geometrical optics, is that at any locations inside this, you still have the total internal reflection, but now there is a multiple possibilities for electrons to be reflected and eventually go to the barrier side. And that what increases the electrical current. Here are some early calculations shown in this paper in 2006. Amount of current enhancement when you use this double zigzag barrier as a function of the period of this zigzag, and it's shown between 0.2 to 1 micron, and as a function of the zigzag height, how deep it is, again between 0.05 micron to 0.4 micron, and you can see you get high enhancement by almost a factor of 60–70%. In the same paper, we also studied the average energy of the moving electrons. Is not only the total current that matters, and even that was enhanced. Again, this is a toy example, but tell you playing with the geometry of the structure can break the symmetry and can enhance the current. This is something that happens quite a bit in actually solar cells and light emitting diodes. They do texturing of the surface to get more light out. Here the idea is that how can we do the same type of texturing to get more electrons out. Let me summarize what you learned in today's lectures. We discuss basically the differences and similarities between vacuum and solid-state thermionics and how this energy conversion happened. We describe how you can model it using Boltzmann transport. I encourage you to go back your notes from week 2 from Mark Lundstrom and see how the same thing can be represented using Landower approach. Later this week we try to connect it as well. We discussed that electron transport in superlattices as well as the Seebeck effect cross-plane can be explained in a mini-band conduction regime, and the theory can explain it. And we also explained the importance of lateral momentum conservation and basically looking at electron populations from different spaces in the real space, energy space and momentum space. That's very instructive. What we will do in the next lecture is we will study what are the thermoelectric effects in some specific indium gallium arsenide and nanoparticle based systems, and how we are able to engineer the thermoelectric properties. I look forward to see you at the next lecture.